Hello and welcome to part 3 of my read and work through of Generating Functionology by Herbert Wilf. Last time I got halfway through section 1.4 and so I'm going to continue. Here is an application star of these results to the theory of spline interpolation. Well, I've never heard of spline interpolation, so let's see. And the footnote was, this application is somewhat specialised and may be omitted at a first reading. Well, I'm going to read it anyway. Suppose we are given a table of values y0, y1 to yn of some function yx at a set of equally spaced points ti is equal to t0 plus IH. We want to construct a smooth function Sx that fits the data subject to the following conditions. So what have we got here? We have y0 to yn, and these are the values of a function yx at t I. So I think we have y at t0 equals y0, y at t1 equals y1, y at tn equals yn. I think that's what they mean. And the ti are equally spaced, so ti equals t0 plus IH. So I'm guessing y is a real valued function, and it's from the real numbers too, presumably the real numbers. We want to construct a smooth function S that fits the data subject to the following conditions. So within each interval ti to ti plus 1, our function S is to be a cubic polynomial, a different one in each interval. The functions Sx, S prime of x and S double prime x are to be continuous on the whole interval t0 to tn. That's both the first and the second derivative of S are going to be continuous, and STI is equal to yi on for I equals 0 to n. A function S that satisfies these three conditions is called a cubic spline. Suppose our unknown spline Sx is given by S0x if x is in the range t0 to t1, S1x if it's in the range t1 to t2, and Sn-1x if it's in the range tn-1 to tn. So we'll have n different cubic subsections, maybe, yeah, the S0 to Sn-1, different cubic functions. And we want now to determine all of the cubic polynomials S0 to Sn-1. To do this, we have two n interpolatory conditions. So Si minus 1, I minus 1, Ti equals yi equals Si Ti. So let's think about this for a second. So S0 is from T0, T1 to, say, the real numbers. So that means that Si is going to be from Ti to Ti minus 1 to the real numbers. And Si minus 1 is going to be from Ti minus 1, the interval from Ti minus 1 to Ti. Yeah, so the biggest value for Si minus 1 can take is Ti, and it will be equal to Si evaluated at Ti as well, so that gives us this equation here, and indeed on the values Ti themselves we do want it to be equal to Yi when we combine them together. Okay, so the ends have to all be the same, and at the ends they have to equal the right Yi. And let's see, for the endpoints they've got S0 T0 equals Y0, and Sn minus 1, this is the far right endpoint, equals Yn. So they say this is 2n conditions. Why is it 2n conditions? We seem to have here n minus 1 conditions and 2 more, so surely that's n plus 1 conditions. Okay, well, I'm just going to keep reading. Along with the 2n minus 2 continuity conditions. So their derivatives have to be equal at adjoins, and so do their second derivatives. So that when we join them all together, S has a derivative and second derivative at the joins. So providing the derivatives are the same, then S will have, at the joins, then S will have a continuous derivative and a continuous second derivative, because cubics always have a continuous first and second derivative. So providing they join, it's going to be continuous, because it's continuous everywhere else. Okay, so the other conditions are, so S prime I minus 1 Ti equals to Si prime Ti, and Si minus 1 double prime Ti is equal to Si double prime Ti. So this is 2n minus 1 conditions. I agree with that, but I don't agree that the first one is 2n conditions. That's strange. It seems to be n plus 1 conditions. Oh no, I see why it's 2n conditions now, because this here is actually 2 conditions, you know, Si minus 1 Ti equals Yi and Si Ti equals Yi. Guess considering that 2 different conditions, so in that case we have 2n minus 1 plus 2, so it's 2n conditions there. So there are altogether 4n minus 2 conditions to satisfy. We have n cubic polynomials to be determined, each of which has 4 coefficients, a total of 4 unknown parameters. Since the conditions are linear, such a spline Sx surely exists, and we can expect it to have two free parameters. So we're after 4n, solving 4n variables, and we've got 4n minus 2 conditions. Well, I mean, it says it's guaranteed to have a solution. However, it's possible that you could have a contradiction. You could have two equal conditions that are asking the same equation to be two different values, but maybe this can't happen in this case. So anyway, assuming that the solution exists, then I agree, it should have two free variables, two free parameters. It is conventional to choose these so that Sx has a point of inflection at t0 and tn. So that means the second derivative is 0 at those points. Okay, so we'll write those two extra conditions down. So so if the derivative isn't, is it defined on the ends? Well, I mean, I guess, yeah, sure. S0, you could, if you want to, you could divide it like this, from minus infinity to t1, and s, they're at n minus 1, aren't they? So s minus 1 could go from ti minus 1 to tn minus 1 to infinity. So it makes sense, if these are cubics, to ask them to have an inflection point, which is 0 at the ends. So that's fair enough. So S0 double prime at, oh no, that should have been T1 after all. Double prime T0 equals 0, and Sn double prime Tn equals 0. So that is another two conditions, two equations. So now we should have a unique solution if there is going to be one, as we'll have 4n equations and 4n variables to determine. So now here is the solution. The functions si are given by what we got here. Six equals, and a load of stuff, okay, so well, I'm just going to copy this down, see if I agree that it roughly makes sense. So Six equals 1 over 6h zi ti plus 1 minus x cubed plus zi plus 1 x minus ti cubed plus 6yi plus 1 minus h squared zi plus 1 x minus ti plus 6yi minus h squared zi ti minus x. Have I copied that down right? Looks okay. Looks okay to me. Then what do we have? So h was was the difference between adjacent TIs. So H is going to be, say, you know, T1 minus T0, because we had that Ti was equal to T0 plus Hi. So I was wondering what H was. And then it says provided that the Zi satisfy Zi minus 1 plus 4Zi plus Zi plus 1 equals 6 over H squared Hi plus 1, sorry, Yi plus 1 minus 2Yi plus Yi minus 1. So these are for I from 1 to n minus 1, and these are for I from 0 to n minus 1. So this is for all of VS. Do we ever have a no, it looks okay. So what we got going on down here, and this is for, this doesn't have I equals 0 here. Yeah, that looks okay. In which case, so for they say, in which case Z0 equals Zn, which is 0. So they say it is easy to check this by substituting x equals Ti and x equals Ti plus 1 into the equation to verify that they're equal to the right values at Ti and Ti plus 1. So well, I can try that. I'm sure that's not too hard. So what do we have here? So if we had Ti in here, well, this would be 0. This term would become 0. So this would be 0. This would be 0. And this would be 0. So what we would have left would be 1 over 6h Zi times Ti plus 1 minus Ti all cubed. And this, Ti plus 1 minus Ti, is going to be h. So we will have Si Ti equals 1 over 6h Zi Ti plus 1 minus Ti cubed equals h squared over 6 Zi. Is that right? No, because I copied my equation down wrong the first time. So Six should have been, that should have been as Ti plus 1, Ti there, Ti here. However, this should have been a Ti plus 1 as well. So Ti plus 1, so therefore I also need to have the term 6Yi minus h squared Yi minus 1. No, I need 6Yi minus h squared Zi times Ti minus Ti plus 1 minus Ti, so that's going to be h as well. So you're also going to have plus 1 over 6h 6Yi minus h squared Zi times h. So what will this work out to be? Let's see if we can simplify this a little bit. It's equal to h squared over 6 zi plus 1 over 6yi minus h squared zi equals h squared over 6zi plus yi minus h squared over 6zi. So this is equal to yi. So indeed, Si evaluated at Ti is yi. Cool. So let's try also. So I didn't at all have to use the simultaneous equations that the Zi satisfy here. Okay, so now I'm going to plug in I plus 1. So Si Ti plus 1. So what we're going to get, we're going to have 1 over 6h. Let's have a look at our equation again. So this is going to be 0. This is going to be 0. So we're only going to be interested in these two terms. So this is going to be zi plus 1 h cubed. So zi plus 1 h cubed plus 6yi plus 1 minus h squared zi plus 1 h. So plus 6yi plus 1 minus h squared zi plus 1 h. Let's see if we can simplify that a little bit. So this is equal to 1 over 6h zi plus 1 h cubed plus 6yi plus 1 minus h cubed zi plus 1. Miss the h out here. This was 6yi plus 1h. Multiplied that, and that was a minus. These terms cancel out, and we get equals 6yi plus 1h over 6h equals yi plus 1. So yeah, that does exactly what it's supposed to do at the ends, and they're all going to do that from S0 up to Sn minus 1. That's going to work. Cool, so they certainly equal the right things. And we've not had to use the simultaneous equations for Z solve yet. So let's keep reading. They say that if the Z satisfy these simultaneous equations, then Z0 and Zn are equal to 0. Are we using that as an assumption? Are we assuming Z0 and Zn are equal to 0 and then solving the equations? So let me think about that. So we're looking for, we're going to have Z0 up to Zn, I think. So Z0, Z1 up to Z. And because in the equation for Si there is both a Zi and a Zi plus 1, and the Si go from S0 up to Sn minus 1, so the Zi must go from Z0 up to Zn. Okay, so there are n plus 1 Zs here, and we are given n minus 1 simultaneous equations, Zi minus 1 plus 4Zi plus Zi plus 1 equals 6 over h squared yi plus 1 minus 2yi plus yi. minus 1, which is n minus 1 equations. So yeah, we can't solve for n plus 1 equations with n minus 1 equations. n plus 1 variables with n minus 1 equations uniquely. So it must be the case. Yeah, so if we let z0 and zn be equal to 0, then if there's going to be a solution here, it's probably going to be a unique one. We would hope, under the right conditions at least. So I'm suspecting that this z0 and zn being equal to 0 is going to relate to the second derivative of the si's, s0 and sn being 0 at the end. That's my guess. So what's next? So it is easy to check this by substituting x equals ti and x equals ti plus 1 to verify that they're equal to, say that si is equal, si ti is equal to yi and si ti plus 1 is equal to yi plus 1, which is we just did. Hence, it remains only to solve the equations 1.4.8. So maybe we should also check that the derivative conditions hold. So let's check that. So if we differentiate with respect to x, let's see. So the term, I'm just going to consider the terms that the x appears in. So we have a ti plus 1 minus x cubed, and if we differentiate that, it's going to be minus 3 ti plus 1 minus x. Now the power comes to the outside, square reduces by 1, and also we have to multiply through by the derivative of the x term here, so we get a minus on the outside. Okay. Other term that occurs is x minus ti cubed, so that's going to differentiate to 3x minus ti squared. Another term is, we don't have any square terms appearing here, it seems. d by dx x minus ti is just going to be 1. Constant term vanishes. And we also have a d by dx, we'll need a d by dx ti plus 1 minus x, which is going to be minus 1. So plugging this back into what we have, so if we differentiate si prime x is going to be 1 over 6h zi times this derivative here, so minus 3zi ti plus 1 minus x squared plus zi plus 1 times this derivative here, so 3zi plus 1 x minus ti squared plus 6yi plus 1 minus h squared zi plus 1 times this derivative of this here, so 1, and then it's going to be plus 6yi minus h squared zi times the derivative of this, which is minus 1. So I'm going to change the plus to a minus there. So shouldn't have not made a mistake. This is derivative of si, so let's try plugging in ti and ti plus 1. Alright, so I really messed up the plugging of ti and ti plus 1 into this equation here, so I'm going to do it again, hopefully without mistakes this time. If you want to see me making mistakes for some reason, then I'm going to upload my first attempt at it in a separate video, if for some reason you're interested in watching me get things wrong. Though I suppose it might be interesting to see how I finally notice my errors and where I realise something is looking a bit strange, which draws my attention to my earlier work in certain places. So let's go through it again, this time hopefully correctly. So this bit was right when I calculated the derivative, so let's plug in ti. This could be 1 over 6h minus 3zi, ti plus 1 minus ti squared, and this bit here is h. This bit is going to become 0, so we just add on the constant terms now, so plus 6yi plus 1 minus h squared zi plus 1 minus 6yi plus h squared zi. Let's simplify this a little. So 1 over 6h minus 3zih squared plus 6 yi plus 1 minus yi. Now, one of the mistakes I made last time was I said that this was h, just like I said that this was h. Obviously that's only true for the ti's, not the yi's. That caused me to waste a lot of time. And minus h squared zi plus 1 plus h squared zi. So rather than add that on again, I'm just going to change this minus 3 to minus 2. So that's fine, we'll leave it like that. And now I'm going, so what we need to do basically is the function s, once we combine all the cubics, it has to have continuous derivative. Now, how do we deal with the derivatives at the points, at the joins? So let's say the function is going to look something like this. Say here is t0, and here is t1, and here is t2. You know, we might have something like that be the S0, first bit of cubic, and then the next one might look something like this. This be S1. Now, obviously, if this is a curve, the derivatives need to be equal at this point. But what does it mean for the derivative to exist at the point? Well, all it means is the derivative from the left and the derivative from the right have to be equal. So, since cubics are differentiable everywhere, then providing the S0 has a derivative at this point at t1 as the same as S1 has its derivative at t1, then we'll be fine. It'll be, it'll be derivative will exist everywhere and be continuous everywhere. So now what we also need to do is calculate si prime ti plus 1. So the other end. So got our equation here. So si prime ti plus 1 equals 1 over 6h. Ti plus 1, this term disappears, and we get 3zi plus 1 h squared, and then add on the constant terms, 6yi plus 1 minus h squared zi plus 1 minus 6yi plus h squared zi. So h squared zi So this time we're going to get 4 h squared z, oops, oh no, we've got minus h squared zi plus 1 there. So we're going to get 2, so it's equal to 1 over 6h, 2zi plus 1 h squared, so we've got this 3zi plus 1 h squared and minus h squared zi plus 1, plus 6 yi plus 1 minus yi, which is not equal to h, plus h squared zi. So what we want, the goal is to have for all I s I prime t I plus 1 to be equal to s I plus 1 prime t I plus 1. So we've just calculated this term. It was this. So this term is equal to this. And this term, well, we just calculated si prime ti, which was back here. So if we just add I to everything there, we'll get this term will be equal to 1 over 6h minus 2zi plus 1 h squared plus 6yi plus 2 minus yi plus 1 minus h squared zi plus 2. So we need this to be equal to this. So that only happens if we have 2zi plus 1 h squared plus 6yi plus 1 minus yi plus h squared zi equals minus 2zi plus 1 h squared plus 6yi plus 2 minus yi plus 1 minus h squared zi plus 2. So this is what we need to hold. Let's rearrange this. We've got 2zi plus 1 h squared here and a minus 2zi plus 1 h squared, so we have 4zi plus 1 h squared. We've got a h squared zi there and a no zi's on the right hand side, so plus h squared zi. We have h squared zi plus 2 on that side and no z plus 2's on the left, so h squared plus h squared zi plus 2. So we've dealt with all the zi's, and so on the right hand side we're going to have 6 yi plus 2 minus yi plus 1 minus yi plus 1 plus yi. So what we have here is h squared zi plus 4zi plus 1 plus zi plus 2 equals 6 yi plus 2 minus 2 yi plus 1 plus yi. Now, we were told that the zi's satisfied the following recurrence relation, the following equations. So zi minus 1 plus 4zi plus zi plus 1 equals 6 over h squared, yi plus 1 minus 2yi plus yi minus 1. And this was supposed to hold for I from 1 to n minus 1. And what do we want this to hold for? Well, we wanted that si prime ti plus 1 equals si plus 1 prime ti plus 1. So we need this to hold for I from 0 up to n minus 2, because in the n minus 2 case you get the n minus 1 there. So go from 0 to n minus 2, then I plus 1 is going to go from 1 to n minus 1. So if we add I 1 to all the i's through here, we have zi plus 4zi plus 1 plus zi plus 2 equals 6 over h squared yi plus 2 minus 2 yi plus 1 plus yi, for I equals 0 to n minus 2. And so that we see that this is true, assuming this holds. So yeah, providing the z's satisfy those equations, then we do indeed have equal derivatives at all the joins. So that's good. So next let's now do the second derivative. So our first derivative was this. Let's try differentiating it. So s double prime I x equals 1 over 6h. We're going to get a minus 2 minus 3, so it's going to become 6 zi ti plus 1 minus x. You're going to get a 2 out here, so it's just going to become plus 6 zi plus 1 x minus ti. And the constant terms that have no x's in, they're just going to vanish. So this is looking nice and simple. So for the second derivatives, we're going to want si double prime ti plus 1 to be equal to si plus 1 double prime ti plus 1 for I equals 0 to n minus 2. Well, so let's try. So si double prime ti plus 1 is going to be equal to 1 over 6h. This bit's going to be 0, so it's going to be 6 zi plus 1 ti plus 1 minus ti, that's just h, so it's equal to zi plus 1. And si plus 1 double prime ti plus 1. Well, instead, I'm going to calculate si double prime ti. So this is going to be 1 over 6h, 6zi, ti plus 1 minus ti, well that's h, and this term is 0. So again, this is zi. So therefore, si plus 1 double prime ti plus 1 equals zi plus 1, which is equal to this, which is equal to si double prime ti plus 1. Okay, so and the last thing, there's one more thing we need to show, is that S0 double prime at t0 equals 0. So S0 double prime at t0, well, Si double prime at ti was equal to Zi. So Si double prime at, so F0 double prime at t0 is equal to Z0, which we're given is 0. And Sn double prime, sorry, Sn minus 1 double prime Tn is going to be equal to Zn equals 0, because S double prime of I get ti plus 1 equals zi plus 1. So yeah, all the conditions hold. Alright, so we've verified that all of the conditions hold when we define SI as they've defined it in 1.4.7. So let's carry on. So hence it remains only to solve the equations 1.4.8. And those were the simultaneous equations zi minus 1 plus 4zi plus zi plus 1 equals 6 over h squared yi plus 1 minus 2yi plus yi minus 1 for n in the range 1 to n minus 1, and z0 is equal to zn is equal to 0. Now, if I remember the example we did at the start of the chapter, which I covered in depth in last video, part 2, we will remember that this was the exact kind of setting we had, where these were UIs in that setting, and this was DI, and we saw how to find a solution and when it was a unique solution, and it revolved around the polynomial, which would have been, in this case, x squared plus 4x plus 1. And if the nth powers of the two roots of this polynomial were different, then we were guaranteed to have a unique solution to this set of equations. So what are the two roots of this polynomial? Let's just check that is going to be the case. So we're going to have minus b, so a, b, c, coefficients of our quadratic, minus b plus or minus square root of b squared minus 4ac all over 2a, which is equal to minus 2 plus or minus the square root of 12 over 2, which is equal to minus 2 plus or minus square root 3. Now, square root of 3 is between 1 and 2. So minus 2 plus square root of 3 is going to be between minus 1 and 0. So in other words, the absolute value of this is less than 1, and minus 2 minus square root of 3 is going to be less than 3, minus 3. So the absolute value of minus 2 minus root 3 is going to be greater than 1. So this tells us that if n is a power, any power greater than 1, then minus 2 plus square root of 3 to the n, the absolute value of that is less than 1, and minus 2 minus square root of 3 to the n, the absolute value is going to be greater than 1. So the nth power of these two roots is always going to be different. So we can always guarantee a solution to this set of equations based on what we did earlier in the section 1.4. So let's see what they say in the book. The system of equations 1.4.8 is of the form 1.4.1, which is what we were just talking about. Hence, we can find the solution from 1.4.3 and 1.4.4. To do this, begin with the given set of points ti, yi, through which we wish to interpolate, and use them to write down. So we're defining the polynomial dx as we did before, which would have been from I equals 1 to n minus 1 di x to the I, where we're letting di be the 6 over h squared yi plus 1 minus 2yi plus yi minus 1. And then they've said since ABC equals 141 in this example, we have R plus and minus is minus 2 plus or minus root 3. Now our unknown generating function, ux, is given by, as we saw in 1.4.3, which reads as they say, ux equals x dx plus z1 plus zn minus 1 x to the n all over 1 plus 4x plus x squared. Yep, I remember that as before. I remember before we had ux over x cx squared plus bx plus a is equal to dx plus u1 plus, so it was, was there a coefficient? It was, I think it was a u1 plus cu, and you used a big N in that example, big N minus 1 x to the n. I remember that was what they had before. So in our case, we're using the same dx, we're using lowercase n in place of uppercase n, and the a, b and c was 1, 4 and 1. So yeah, that's how you get that. And they're plugging in the two roots, r plus and r minus, to get a pair of simultaneous equations. So let's see, I think that's what they're doing here. So if we plug in, say r plus equals minus 2 plus square root of 3, so we would have 0. So plugging it into this thing here, we're going to have 0 on the left equals d r plus z1 plus zn minus 1 r plus to the n, and the other equation is going to be, if you plug in r minus equals minus 2 minus root 3, 0 equals dr minus plus z1 plus zn minus 1 r minus to the n. And of course we can use these to solve for z1 and zn minus 1. So what's it say next? When we know ux, which is, after all, the sum from I equals 1 to n minus 1 zi, we can read off its coefficients to find all of the z's and use them in 1.4.7 to find the interpolating splines. So yeah, once we know all the z's, we know all of the si's. Okay, so that's the end of that section. As I say, you know, we know that this is going to solve because we know these two are different, they're not equal. And well, I mean, this again in the book, it's incomplete here because they never proved the existence of a solution given the condition that the nth power of the two roots of that polynomial are different. All they proved is that if one exists, then it's unique. But in the last video, we filled in that gap. So we know that this is going to work. So while that was a completely valid proof for why there exists this spline and it's unique, I was wondering where precisely this magic formula they came out with came from. Once you have this formula, plugging all the values ti plus 1 and showing that everything is verified and works suffices to prove the thing. But where did he get this from in the first place? Well, I played around a little bit. It's not too hard to work out yourself, so I'll just quickly show you that. So firstly, all of the SIX are cubics, and what I'm going to do is, like they did, I'm going to let zi be the second derivative of si at ti, and then we also require that zi plus 1 is equal to the second derivative of ti plus 1. This is something that's going to have to hold whatever the values of z are. Now, since SIX is a cubic, SI double prime x is a linear function, and if we know if we've got a linear function, so if AX say is linear, and we know AX at two different points, call them x1 and x2. So if x1 equals y1 and x2 equals y2, then provided that x1 and x2 are different, let's suppose, just provided that x1 and x2 are different, then we have that AX is equal to y1 over x2 minus x1, x minus x2 plus y2 over x2 minus x1, x minus x1. So you see that when x is equal to x1, this part becomes this becomes 0, this becomes x1 minus x2. Oh, I needed a minus here. So this bit becomes x1 minus x2 over x2 minus x1. It's minus 1, so it becomes y1. And when x is equal to x2, this part becomes 0, and this part becomes y2. So we're going to use this fact here, and we know that SI double prime is linear, and we know its value at two different points, and therefore we have SI double prime x is equal to, so we have the y2, which I'm going to call replace it with zi plus 1, over x2 minus x1, well in this case that's ti plus 1 minus ti, it's just h over h, times x minus x1, which in this case is the t1. And we're going to have minus zi over h x minus ti plus 1. That was ti, that was supposed to be ti. So let's just check this works. So when x is equal to ti, this is 0 and this is minus h over h times minus zi. That's zi, that's correct. And when x is equal to ti plus 1, this bit's 0 and you get h over h times zi plus 1. So we know that the second derivative of si is equal to that. So if we integrate it twice, we'll obtain let's integrate this twice. We obtain that si is equal to six is equal to zi plus 1 over 6h x minus ti cubed minus zi over 6h x minus ti plus 1 cubed plus ax, where ax is some unknown linear function obtained from the unknown constant that you get each time you integrate. So what we're going to do now is we'll do the same trick again, except here ax is our linear function. So what we do is we know that si at ti is yi and si at ti plus 1 is yi plus 1. So let's plug that in and see what we get. So we get si at ti, this is 0, so this is minus zi over 6h, and this is going to be minus h cubed plus ati is equal to yi. So we know that a evaluated at ti is equal to yi minus zi over 6h cubed, and also we know that si evaluated at ti plus 1. So here's si, so at ti plus 1, this is going to be zi plus 1 over 6h cubed, this is 0, plus a ti plus 1, so equal to zi plus 1 over 6h cubed plus a ti plus 1 equals yi plus 1. So a ti plus 1 equals yi plus 1 minus zi plus 1 over 6h cubed. So I'm going to cancel these h's out. You've got h here, so yeah, h squared. So it's y, ati is yi minus zi over 6h squared, and ati plus 1 is yi plus 1 minus zi plus 1 times h squared over 6. So since we know that a is a linear function, we can say that ax is equal to yi plus 1 minus zi plus 1 h squared over 6 times x minus ti, and we need a 1 over h here, minus 1 over h yi minus zi over 6 h squared x minus ti plus 1. Yeah, we just check. So we're a at ti, this is going to be minus h over h, so we just get this bit, which is what we're supposed to get. And a at ti plus 1, this is 0, you just get h over h, so you just get this bit here. So yeah, that's right. So we have worked out what si must be. So we had six is equal to this thing, and we know what AX is now. So plugging all that together, we will get, so SIX equals, let's take the 1 over 6h out because that's the form they had it in, so 1 over 6h zi plus 1 x minus ti cubed plus zi ti plus 1 minus x cubed plus ax. What was ax? Ax is here. So, and we remember we took 6h out, so well, it's 1 over h is here, but we need a 6 as well. So we have plus 6yi plus 1 minus zi plus 1 h squared x minus ti plus 6yi, sorry, that was meant to be a minus, 6yi minus zi h squared x minus ti plus 1. And is that exactly what they have? Let's see. They have a zi plus 1 x minus ti cubed. They have a zi ti plus 1 minus x cubed. And they have a 6yi plus 1 minus h squared zi plus 1 and times x minus ti. And then they have minus oh, if we don't have minus, they've written a plus, but they've swapped this around, so ti minus x, something like that. So yeah, it's right. So that's how you get what they have. And then for the extra condition that the derivatives s prime I ti plus 1 has to be equal to s prime I plus 1 ti plus 1. You differentiate this, plug in these two values, and then you get the rule that the z's have to satisfy, which was the case that we covered earlier in this section. So yeah, that's how you can work out this form for the SIX if you weren't given it in the first place. Alright, so we're on to the last section of part of section 1.4, the example. So let's see. Now let's try an example with real live numbers in it. Suppose we are trying to fit the powers of 2 by a cubic spline on the interval 0 to 5. So we're going to want a function SX from 0 to 5 to the real numbers, such that I guess we're going to use the integers, so h being 1, s0 equals 1, s1 equals 2, s2 equals 4, s3 equals 8, s4 equals 16, and s5 equals 32. Okay. So our input data are yi equals 2 to the I for I in the range 0, 1, 2, 5. The ti are I for I in the range 0, 1, 2, 5. So from 1.4.9 we find that dx is equal to dx, what was dx? What did we do? We had that dx was 6 over h squared, sum from I equals 1 to n minus 1, so 4 in this case, yi plus 1 minus 2yi plus yi minus 1 x to the I. So this is 6 over h squared, I from 1 to 4, 2 to the I plus 1 minus 2 times 2 to the I plus 2 to the I minus 1 x to the I equals 6 over h squared, I equal I from 1 to 4, these two terms cancel, so 2 to the I minus 1 xi, which equals, so h was 1 because we're taking our ti's to be going from 0 to 5, so this is just 6 times I equals, I goes from 1 to 4, so the first value is 2 to the 0, so we'll have x plus 2x squared plus 4x cubed plus 8x to the 4. That's our dx. And that's what they've got written down. Then we solve 1.4.11 to find that z1 equals 204 over 209 and z4 equals 2370 over 209. So I was playing around trying to find the values of z1, z2, z3, z4 just as they did in the book, and I found a few tricks along the way to enable one to calculate these things a little more easily. So I started off with dx being 6x 1 plus 2x plus 4x squared plus 8x cubed, and the simultaneous equations, which are, so 0 is equal to dr plus z1 plus z4 r plus to the 5 and dr minus plus z4 z1 plus z4 r minus to the 5. And I started off by trying to calculate z4 by finding the difference between the two equations. So we get z4 r plus 5 minus r minus to the 5 plus dr plus minus dr minus equals 0. So it's just the difference between the two equations there. And so z4 equals minus dr plus minus dr minus over r plus to the 5th power and r minus r minus to the 5. And so we immediately see that it looks as though it's going to be a little bit tricky, because our r plus minus was minus 2 plus or minus the square root of 3, and taking the 5th power of this, taking the first, second, third powers of it and adding them together is going to be a pain, basically. So I was playing around with it, and first trick I noticed was that it's easier to just work with the differences. So r plus to the n minus r minus to the n, because if we unpack this, the r's only ever occur in this form. So for example, the rewriting this out, we have z4 equals minus and dr plus, so we're going to have 6r plus 2r plus squared plus 4r plus cubed plus 8r plus to the 4 minus dr minus, so keep the 6 on the outside, minus r minus 2r minus squared minus 4r minus cubed minus 8r minus to the 4, and then we have over r plus to the 5 minus r minus to the 5. So basically this is minus 6 r plus minus r minus plus 2 r plus squared minus r minus squared plus 4 r plus cubed minus r minus cubed plus 8 r plus to the 4 minus r minus to the 4 all over r plus to the 5 minus r minus to the 5. So I first started playing around with this, and I found that works quite well to an extent. So to get, we can get quite a nice simple way of calculating the differences between the two powers, between the powers of the two roots quite easily, by noting that if r is a root, of a polynomial x squared plus 4x plus 1, then r satisfies r plus r squared plus 4r plus 1 equals 0. And this obviously holds for both r plus and r minus because they're both roots of this. And furthermore, if we multiply through this equation here by any power of r, we have that r2 plus n, say, plus 4r 1 plus n plus r to the n is equal to 0. So this gives us a recurrence relation for powers of the roots of a polynomial. So for example, if we know, so if we want to know r plus to the n plus 1, well, if we know r plus to the n and r plus to the n minus 1, it's just r plus to the n minus 1 is equal to minus 4 r plus to the n minus r minus to the n minus 1. And this obviously also holds for the other root, r minus to the n minus 1 equals minus 4 r minus to the n minus r minus to the n minus 1. And therefore any linear combination of r plus and powers of r plus and r minus are going to follow this also. So for example, the difference between them, r plus to the n plus 1 minus r minus to the n plus 1 equals minus 4 r plus to the n minus r minus to the n minus r minus to the n minus 1 minus r minus to the n minus 1. That should have been an r plus. So with this, it becomes fairly simple to calculate all of these differences here. So, and this turns out to be much simpler than just calculating the powers r plus to the 5 and r minus to the 5 individually and then finding their difference. That turns out to be a pain. It's much easier to do it like this. So we'll see why. If we consider n equals 0, we have r plus to the 0 minus r minus to the 0. It's 1 minus 1. That's just 0. And if instead we consider n equals 2, r plus to the 1 minus r minus to the 1 equals 2 root 3. Now, if instead I can consider the sequence r plus to the n minus r minus to the n divided by 2 root 3, then it's still going to satisfy the same recurrence relation. So if I say let un equals this, we know that u0 is equal to 0, and u1 equals 2 root 3 over 2 root 3 equals 1. And u is going to satisfy the same recurrence relation, so un plus 1 equals minus 4un minus un minus 1, and therefore it's very easy to calculate the first n terms, so the first 5, so 0, 1, 2, 3, 4, 5, and un 0, 1, first two terms, and so it's minus 4 times this, minus this, so it's minus 4, then it's going to be 16 minus 1, 15, it's going to be minus 60 plus 4, 50 minus 56, and then it's going to be 224 minus 15, 209. So for example, we know that u5 equals 209, and u5 was r plus to the 5 minus r minus to the 5 over 2 root 3. So we now know what r plus to the 5 minus r minus to the 5 is. We just multiply 209 by 2 root 3. Though we won't ever need to use this 2 root 3, and I'll show you why. So we had that Z4 was equal to this here. So I extracted all the r pluses and r minuses out and combine them together with matching powers like this. And if I divide the top and the bottom of this equation here by 2 root 3, we can then say that Z4 is equal to minus 6 times u1 plus 2u2 plus 4u3 plus 8u4 divided by u5. So we have a very nice simple way now of calculating Z4. So, well, let's do it. We've got all these numbers. So Z4 is going to be equal to 6 times, would be minus 6. Is there a minus? Yep, there's a minus. So minus 6 times so it was u1 plus, so it's u1 plus 2u2, so minus 8, plus 4u3 plus 60 minus 8u4 minus 8 times 56, and over u5 over 209. So if we work out these, I'm just going to put it into a calculator because I can't be bothered to work that out by hand. You get minus 6 times minus 395 over 209, which is 2,370 over 209, which is what they've got in the book. So after I'd done this, I was quite pleased with that. I then tried to work out Z1, and I wanted to find a similar nice easy trick for doing Z1. So first I just tried plugging Z4, equation for Z4, straight back into one of our earlier equations. So you know, we had these two equations here, so we could say take first one, so 0 equals dr plus z1 plus z4r plus to the 5, and we remember that z4 was minus dr plus minus dr minus over r plus to the 5, r minus to the 5. So if I plug this into this equation here, we get that 0 equals dr plus plus z1 minus r plus to the 5 dr plus r plus to the 5 dr minus over r plus to the 5 minus r minus to the 5. So z1 is equal to r plus to the 5 dr plus minus r plus to the 5 dr minus r plus to the 5 minus r minus to the 5 dr plus all over r plus to the 5 minus r minus to the 5, which is equal to, so some things are going to cancel out here. We've got an r plus to the 5 dr, and here we've got a r plus to the minus r plus to the 5 dr. So this term and this term is going to cancel. So what we're left with is r minus to the 5 dr plus minus r plus to the 5 dr minus over r plus to the 5 minus r minus to the 5. So we have this equation here. And this at first didn't look quite so useful as the previous form we got, because we're going to have r minus to the 5 multiplied by powers of r plus, and it's not looking quite so nice. But we have a nice fact about our r plus and r minus. So our r plus times r minus, which is minus 2 plus square root of 3 times minus 2 minus the square root of 3, which is equal to minus 2 squared minus the square root of 3 squared. Difference between 3 squared is 1. So r plus is the inverse of r minus, and r minus is the inverse of r plus, and their product is 1. So that's quite a nice thing. So what we're going to do here is we've got our equation for z1, and we divide the top and the bottom by r plus r minus to the 5. So which is 1 basically, but what we end up with is r plus to the minus 5 dr plus minus r minus to the minus 5 dr minus over r minus to the minus 5 minus r plus to the minus 5. And since r plus and r minus are self-inversive, I can say this is actually r plus to the 5 minus r minus to the 5. And looking at this here, looking at these terms here, the top of this is going to be, so the sum from I equals 1 to 4 of di, and then we're going to have r plus to the I minus 5 minus r minus to the I minus 5 over r plus to the 5 minus r minus to the 5. And again, using the fact that the Ri is the inverse of r minus is the inverse of r plus, this becomes the sum of di of r minus 5 minus I, so we've got positive indexes now, r minus r plus 5 minus I over r plus to the 5 minus r minus to the 5. And then now it's looking good again, because all now we have is differences between powers of r plus and r minus, which we know all about already. So in this case, what we're going to have is it's going to be d1 u4 plus d2 u3 plus d3 u2 plus d2 u1 over u5, once we've divided the top and the bottom by 2 root 3. So let's plug the values in here and see what we get. So let's just remember u1 was equal to 1, u2 was equal to minus 4, u3 was equal to 15, u4 was minus 56, and u5 was 209. So plugging these in, well, what we're going to get is minus 56 plus d2, so d2 was 2 plus 2 times 15 is 30, d3 was 4, so plus 4 times minus 4, so minus 16, and d4 was 8, so we're going to have 8 times 1 plus 8, and this can be over 209. There was a factor of 6, sorry, because di is 6 times 2 to the I minus 1. So let's see what we get here. Plug this value into a calculator. I needed a minus outside here as well. The whole thing was negative because here we had r minus to a power minus r plus to the power, so to swap them around to get r plus to a power minus r minus to the power, we need to multiply through by minus 1. So what we get here is minus 6 times, so let's put this into a calculator, minus 56 plus 30 minus 16 plus 8. Minus 6 times minus 34 over 209 equals 204 over 209, which again is exactly what they had in the book, so that works out in the end. And this got me thinking, these two forms that we have for Z1 and Zn, they're remarkably similar. So for instance, all Z4 was, it was 6 times, it's minus 6 times a sum from 1 to 4 of di di times ui over u to the 5, and Z1 was equal to minus 6 times the sum from I equals 1 to 4 d 5 minus I ui over u5. And so this got me thinking, using some sort of rearranging, is it possible to use the same trick to get the Z2, Z3 in some sort of nice form that we can quickly compute, as I did just from using our sequence U1, U2, U3, U4, U5? And it turns out that there is, and it took me a little while, and I've typed some of it up, but this video has gone on long enough as it is, so I'm going to leave it there, and I'll discuss this further in the next video. So thank you for following and watching this video. If you've made it this far, well done. See you next time.